Excuse me. Okay, we left off here at section 7.10, which deals with other substrates. So far, the only substrates, and substrate just means our starting material, the only substrate we've really talked about has been alkyl halides, where the leaving group was either an iodide or a bromide or a chloride. Those were the leaving groups that we saw. But now we're going to see that we can have different substrates that can undergo substitution and elimination reactions, and those other substrates that we're interested in are called alkyl sulfonates. And we have three different types of alkyl sulfonates shown right here. You notice what they all have in common is that they have your alkyl group followed by an oxygen. Let me use a different color. Followed by an oxygen bound to a sulfur with two double bonds to oxygen. So you have all of that in all of them. So this means they're all alkyl sulfonates. But you see that the sulfonates change. In the one furthest to the left, we have a methyl sulfonate. We call that a mesylate. And the abbreviation we use for that is, excuse me, O. And then all of this is MS, so a mesylate. The next one has a toluene. So when you have a benzene ring, so when you have an aromatic ring like this and you have a methyl group attached to it, this is called toluene. Toluene. So this is a toluene group over here, and we call that a tosylate. We abbreviate that OTS. So a tosylate group. So we have a mesylate, which has a methyl group. Oops. And then we have a toluene, which has a tosylate. And the last one has a trifluoromethyl, and we call that a triflate. So a triflate group, and we abbreviate that OTF. So we've got OTS, OTF, and OMS, and they're all good leaving groups. In fact, they are described here as excellent leaving groups. Now, what was the criteria that we had for a good leaving group? It had to be the conjugate base of a strong acid. And if you draw the conjugate acid of a mesylate, a tosylate, and a triflate, what you'll see is that they're all strong acids. Now, why would they be good, excuse me, good leaving groups? It's because after they leave, they form a resonance stabilized anion. And you could draw the conjugate base of the mesylate, the tosylate, and the triflate, and you could draw the resonance structures for any one of their conjugate bases. But if we look at the pKa values of their conjugate acids, the mesylate's conjugate acid is methane sulfonic acid. The tosylate's conjugate acid is toluene sulfonic acid. And the triflate ion is the conjugate base of trifluoromethane sulfonic acid. Could anybody answer this question? Based on pKa values, which one would be the best leaving group? Would it be the OMS, the OTS, or the OTF? Mesylate, tosylate, or triflate? Could anybody answer that? Best leaving group of all. Yes, thanks, Clinton. It's going to be the triflate. The best leaving group on here is going to be the OTF, would be the best leaving group. Why? Because it is the conjugate base of the strongest acid. Trifluoromethane sulfonic acid, if you look at this, this is 10,000 times a stronger acid than, or sorry, 100,000 times stronger than sulfuric acid. That's serious, right? That's a huge difference in acidity. But either way, they all have pKa values that are less than 0, and thus they're all considered strong acids, and thus the OTS, the OTF, and the TS, or sorry, the OMS are all good leaving groups. Now, even though the OTF is the strongest or the weakest of all the bases, therefore the best leaving group, the one that we're going to use the most is going to be the tosylate. And the reason why is because the tosylate, if you use tosyl chloride, which is used to make the tosylate, it's a solid at room temperature, this compound, so it's a lot easier to work with than the triflate. So sulfonates are made from the corresponding alcohol. And this is something that we're going to talk about again in chapter 12 in organic chemistry 2. We're going to do all kinds of alcohol chemistry. So to add the tosylate, to the alcohol, or in other words, to convert this into a good leaving group, you treat it with toluene chloride, which forms this oxonium ion, right? It just does a nucleophilic attack. We lose our leaving group. And then pyridine comes in and acts as a base, removes the proton from the oxonium ion to form our ROTS, our good leaving group. So what we're doing is we're taking a poor leaving group, and we're adding the tosylate, and we're converting it to a good leaving group. So realize that we're just strapping on the TS group to the oxygen of the alcohol, and therefore, if your alcohol is on a chiral center, it's not going to change the chirality of that center whatsoever. So if you start with S, you'd end up with S. Now, since you're using toluene chloride followed by pyridine, you actually are using them together. So the reagents that we write are TSCl for toluene chloride and PY, which represents pyridine. It's just a shorthand that we use for pyridine, our base. So again, we go from a crummy leaving group to a great leaving group. So what do we know? If we have a substrate that's got a great leaving group, we can do Sn2 and E2 reactions on it. And we find that if you have a primary tosylate and you treat it with hydroxide, which is a strong base, but it's also a strong nucleophile, you end up with a mixture of E2 and Sn2 products. However, since the substrate is primary, the Sn2 product is going to predominate. Whereas if you have a secondary alkyl halide, since again you're treating it with alkyl halide, a secondary tosylate, since you're treating it with a strong base, strong nucleophile, you're going to get a mixture of elimination and substitution again, but now the elimination is going to predominate. So it behaves much in the same way that an alkyl halide would. And so with all that in mind, why don't we try a couple of practice problems? If we look at the first one, we have a secondary tosylate. So this would be secondary. We're treating it with ethoxide, which is a strong base, and it's also a strong nucleophile. And so since it's secondary, like we saw on the previous slide, we're going to get a mixture of E2 and Sn2, and E2 is going to be the major product. So our E2 product, the only product we could form, E2, would be cyclohexene. And for the Sn2, there's no steric center to even worry about. And so our Sn2 product is just going to look like this. We have our nucleophilic attack and loss of leaving group, and we would replace the tosylate with an ethyl group. The next one is also secondary, and we're treating it with a strong base, strong nucleophile. And so E2 will predominate, but we'll also get some Sn2. Again, the E2 is going to be the major product, but now we've got regioisomers and stereoisomers that can be formed because we have so many beta protons. We have these protons on this methyl group on the end. If we were to rip one of those off, we'd have 1, 2, 3, 4, 5, 6. We'd have our double bond here. But if we pull them off the beta proton, or off of this beta carbon, we can end up with a mixture of cis and trans. So let's draw both of them. I'll start by drawing the trans, which should be this 1, 2, 3, 4, 5, 6. And then we're also going to get the cis 1, 2, 3, 4, 5, 6, like that. Now, out of those three alkenes, could anybody tell me which one of those would be the major E2 product? Would it be the red one, the black one, or the blue one? And again, there's no trick questions in organic chemistry. Which one would be the major product here? It's going to be the black one, isn't it? Right? Thanks, Kiana. This will be the major product because it's the most substituted of all. All right, and then we're also going to get some Sn2, and that's going to occur via inversion of configuration because we do have a stereo center. So our Sn2 product is going to look like this, 1, 2, 3, 4, 5, 6. And now our wedge is going to be converted into a dash, and we'll have our alcohol on there. So again, all of these are the E2 products. This is our major product, the one I have in the black box. And this one here is going to be our Sn2 product, which proceeded through inversion of configuration. What are some other ways that we can make good leaving groups? Well, it just so happens that if we have an alcohol, a hydroxide by itself, or hydroxyl, is a poor leaving group. Poor leaving group, just put here poor Lg, poor leaving group. However, we see that the hydroxyl becomes substituted with a bromine when we treat a primary alcohol with HBr. Well, why would that be? I thought you said that you couldn't undergo substitution with a poor leaving group. Well, hold on. What happens, since we're using HBr, which is such a strong acid, it can protonate the alcohol to take this poor leaving group and convert it into a great leaving group. So we'll put here good leaving group, right? Because it converts it into a leaving group, and we know that water is a great leaving group. Water is the conjugate base of hydronium, which is a strong acid. So once you've protonated this and made the oxonium, then bromide can come in, and we get our nucleophilic attack, followed by loss of leaving group occurring simultaneously. And there we found a way to convert a primary alcohol into a primary bromide. Well, what about an Sn1 process? Could you do that? If you have a tertiary alcohol, you can do an Sn1 process. Why? Because you can take this crummy leaving group. Again, there's our poor leaving group, and it's a tertiary alcohol this time. And so if we protonate it, we convert the alcohol into a good leaving group, which can leave to form our carbocation, which can then undergo nucleophilic attack via the bromide. Again, strongly acidic conditions. These are protic conditions. They favor Sn1. And finally, if we have an alcohol, we can also cause an alcohol to undergo an E1 elimination. Well, how would that work? If you have a tertiary alcohol and you just cook it up with sulfuric acid and heat, I'd have to say that this is one of my favorite reactions in the entire course. I know you're tired of hearing new reactions, but this might be my favorite. I'll put here favorite, question mark. I love this reaction. It's so simple and effective. All you need is sulfuric acid and a heater. You just heat it up in sulfuric acid, and it does an E1 elimination. And you always end up with the more substituted alkene. So we'll put here most substituted alkene. Now, there's only one alkene that can be formed in this particular example. But the way that it works is you take the strong acid, which protonates your alcohol, which again is a poor leaving group, and it converts it into a great leaving group. Good leaving group, but again, it's tertiary, so it can leave to form a carbocation, which can then undergo a proton transfer to give you an alkene. A very neat reaction. And so if we wanted to draw a plausible mechanism for this reaction here, we have a tertiary alcohol, and we see that it's undergoing a substitution where we're adding a bromine. So what's going to happen in the first step is we're going to take the alcohol, which is a terrible leaving group, very crummy leaving group, and we're going to convert it into a great leaving group by protonating it with hydrobromic acid. So we're going to add a proton here, and now we've made a great leaving group, or a good leaving group at least. So our leaving group can leave because this is tertiary, and we end up, after it leaves, forming a tertiary carbocation. Well, now that I have the tertiary carbocation, you see that I formed bromide over here. And so my bromide can come in as my nucleophile, and I'm going to get a nucleophilic attack occurring. There's no stereocenter formed in this specific example, and I'm going to end up with this compound with my bromine here. So that would be a reasonable mechanism for this reaction. So this would be an Sn1 mechanism, one at a time. We get loss of leaving group here, and we get nucleophilic attack occurring here after you convert the poor leaving group into a good leaving group. Let's try another one to see if we can draw a mechanism for the formation of this alkene. We're taking a secondary alcohol and we're treating it with sulfuric acid. Well, what happens if you take an alcohol and you put it in sulfuric acid? You protonate that alcohol to convert it from a poor leaving group into a good leaving group. So what's going to happen here? Let's draw it out. We're going to have our alcohol, and it's going to undergo protonation via the acid. Now, what's the major acid that we have in here? Remember, you're in concentrated sulfuric acid. Sulfuric acid is found in water, and that's going to lie to the side of hydronium plus the hydrogen sulfate ion. So I'm going to draw hydronium as my acid since it's what's present in a larger amount. And we're going to draw the proton transfer that converts that alcohol from a poor leaving group into a good leaving group. So now it's a good leaving group and it's going to leave. And when it leaves, we end up forming a secondary carbocation. And we see that this is going to undergo a methide shift to give us a tertiary carbocation that looks like that. So you go from secondary carbocation to tertiary carbocation via this rearrangement. And now we can do a proton transfer where we remove this proton that I'm going to highlight in blue. So now our water molecule is going to come in and it's going to grab that proton and we're going to form the double bond in this E1, in this E1 reaction. So this would be considered an E1 mechanism. The first step is the loss of leaving group, followed by the proton transfer in an elimination reaction. But of course, that occurs after we convert the poor leaving group into a good leaving group. The same thing that we saw before. So the last thing I'll tell you before we get into our weekend break is the whole point of organic synthesis, as I mentioned to you before the lecture started today, is to make valuable, complex compounds from something that's cheap and readily available. And when I say valuable compounds, it could be a compound used in a material to make, any kind of device, but it's oftentimes used to make medicines that are used to extend and enhance a human life. And so if we have a good substrate, like a primary alkyl halide, it can undergo an Sn2 with a hydroxide to make an alcohol. That alcohol can be treated with HBr to be converted into a good leaving group, and we can do an Sn2 to make an alkyl halide. We can form a tosylate from an alcohol with tosyl chloride and pyridine. It can undergo an Sn2 if we have a primary tosylate to produce an alcohol. We can treat the tosylate with a hindered base like T-butoxide, which isn't going to do any substitution. It's only going to form an alkene via elimination. We could also take our alkyl halide and treat it with a strong base poor nucleophile to make an alkene. We could treat it with an alkoxide to make an ether. We could treat it with hydrosulfide to make a thiol. We could treat it with the conjugate base of acetic acid. So this is an acetate. This is something you should have seen a lot of in general chemistry too. And that would do just a plain old Sn2 reaction. And now you've made an ester. And then you could also use cyanide, and I'll draw the cyanide ion out for you. Cyanide is also a good nucleophile, and that could do an Sn2. I'll fix my arrow here. That could do an Sn2 to make a nitrile. So now we've got a whole bunch of ways to make different functional groups. What if you have a tertiary leaving group? Well, if you have a tertiary leaving group and you treat it with that tertiary leaving group with a hindered base, you're going to get a Hofmann alkene. If you treat it with a non-hindered base, you're going to get the Zaitsev alkene. What else could you do? You could do a solvolysis reaction to make an alcohol. And you could take the alcohol and do an Sn1 reaction to make an alkyl halide. You could take a tertiary alcohol, convert it into a tosylate, which is a good leaving group. Once you have that, you can treat it with a hindered base to make the Hofmann alkene. You could treat it with an unhindered base to make the Zaitsev alkene. And then, of course, my favorite reaction is you just cook it up in sulfuric acid and you end up with only the most substituted alkene. So now we've seen a bunch of cool reactions that we can do with tertiary alkyl halides and tertiary tosylate.